Do you know what is ECO? That is Engineering Change Order in VLSI. Do you know whether the ECO is done in the front end or in the back end? Do you know that the ECO can be invoked from multiple stages in the entire VLSI design flow? Stay tuned till the end of the video to know all the answers.
Hey guys, welcome back. In today's episode, we are going to discuss the below points. First, introduction. We will introduce you to the concept of the engineering change order. Next, we will show you the entire VLSI ASIC design flow and also point out what type of ECO is done in which section. Next, we will talk about the pre-mask ECO flow, and next we will elaborate the post-mask ECO flow. Next, we will categorize the types of ECO based on the design stage. Next, we will talk about different types of ECO based on the analysis, that is the detection method. Next, we will talk about the ECO target detection through analysis. Here we will talk about the detection of the ECO violation through different analysis which we have talked about here, and we will show the methodology through which generally an engineer does find out the proper ECO violations and avoid any false alarm. Finally, we will take a short tour on various ECO cells like spare cells, Re-Configurable cells and gate array cells, so that you are very much familiar with what type of cells are used in proper ECO. And this way, we will cover our today's episode about the ECO. Here we are done with the menu slide. Without any further delay, let's begin. Introduction. Engineering change order ECO is a bug fix method on actual chip design and or with layout with minimum disturbance and the existing implementation. So why we call it a bug fix? Because this fixes any design errors that is coming out because of the implementation process through which we include the BUL, FUL and MUL, all these things. And in process of that, implementing all these BUL, MUL and FUL, what happens that because of the methodology of implementation of all these layers, error may come out and that might show up in the actual silicon fabrication. This is not a specification related error of a design. Rather, when we are doing the implementation, that is the physical design, things may goof up due to the entire process because there will be multi-million gates in a modern ASIC chip and those gates gets interconnected through the implementation process. The connection procedure is not a very easy one. There will be congestion and lot of complexities will be there. So I have already talked about different type of violations in this FAQ series like airdrop violation and others, and also there will be the various rules that have to be passed for the physical verification. And when these steps are multiple times iterated, we implement delta changes, and because of those delta changes, somewhere something may goof up which may actually get popped up on the silicon, not before that. How they can show up in the silicon? We have to do the ECO process. So we will talk about various methodologies today, how the things can be preventively taken care. Helps in saving turnaround time and already spent optimization effort and hours at various stages of the design. This is what I have just talked about, because in implementation it takes hours, it takes days and it takes months to implement things in the physical design. Due to continuous increase in the design complexity, the metal mask ECOs have become inevitable. So we will talk about the metal mask ECOs later on. ECOs accommodate design specification changes for various reasons. These include rectification of functional errors, also include non-functional design requirements such as timing and power. In present days, the EDA tool vendors provide inbuilt ECO solutions. This is a very important point. We'll come up with these things and how we deal with such inbuilt ECO solutions and how we actually implement them in later slides. In addition, customized scripts can be there to improve due to the ECO's high computational complexity and algorithm. Sometimes the company provided, that means the vendor provided ECO solution through the EDA tools is sufficient, and sometimes we have to also implement the customized scripts, that is user defined scripts, to make the things over sanguine, so that we are over sanguine that there is no ECO related error left behind. It also possible to include engineering change order ECOs even after the first step out. So this is one thing, because this is a way of catching the bugs, and sometimes it may happen the silicon has been taped out and then the ECOs have been showed up. VLSI ASIC design flow and ECO. So here we will show you the VLSI ASIC design flow, and also grossly we will show what type of ECO is done at what stage. First is the design specification, through which what we design is defined. The flow proceeds in the direction of the arrow, and next we have RTL coding, next we have the verification, synthesis, then we have DFT or scan chain insertion, next we have the floor planning. So up to this we are on the front end side. Now we are entering into the back end side from here, floor planning. Next we have power planning or routing. We have global placement, we have detailed placement, and then we proceed with the clock tree synthesis. And now our flow goes in the direction of the arrow, that is this arrow. Next we have global and detailed routing. We have layout generation and changes. We have DRC and LBS. We have parasitic extraction. We have static timing analysis, that is the post layout static timing analysis. Although we may have a static timing analysis in the pre-layout part, which is called pre-layout static timing analysis, but mostly the post layout static timing analysis helps in the debug for the timing related, that is the performance related error, because of the parasitics coming into the picture because of the physical design in the layout or after the layout. Next we have EM and IR analysis. Next we have the LEC and final tape out checks. And finally, we proceed for the tape out. Now, you can see there is a lot of physical design checks right here. Rather, I include this. There will be a lot of rotation in between. There will be a lot of rotation. And in this rotation, the implementation that has been started from here will get impacted. And reiteration at any stage like this, or whatever will introduce chances of having problems in the design, which may require the engineering change order before we tape out. Generally, these things are checked before we tape out. Once the tape out is done, right, it goes to the foundry and the chip is ready for production. So whatever we have to do before the tape out. Although ECOs are done even after the tape out, if some bug has been slipped out, even very thorough precautionary measure in the ECO. Now this is our VLSI ASIC chip design flow. We have separated out the front end and the back end. So anything above here is the front end and anything up to this is back end. Now there will be a pre-mask ECO. Before the mask has been made, there will be a pre-mask ECO. And similarly, there will be a post-mask ECO. So once the mask has been made. So what is a mask? Generally, the layout is the mask because it goes to the foundry in form of various masks. Layout is nothing but the superposition of the actual devices in terms of mask. You are very much familiar with the stick diagrams and all, and full implementation level that is implemented as the layout, and that is nothing but the mask. So we have two types of ECOs. One is a pre-mask ECO and a mask. So I have placed them side by side so that you can understand which is related to where. So this is related to this zone, right? This zone, and this post mask ECO is related with this. Next, we have the problems like if we can have the bugs from the RTL stage, from the synthesis stage. From there, the bugs can still remain. And what we do, we also have some ECO cells ready with us that they can be used. And in the post-mask ECO, there could be a metal-only ECO. So metal-only ECO means we are talking about the BEOL, right? We have already one episode on FUL, BEOL and MEOL. In this same FAQ series, in case you do not know about these things, please go ahead and watch them. We are talking about the BEOL metal layers, and there we can do the changes with the metal-only changes in the ECO. And also we have spare cells. Spare cells are used like generally the ECO is done in the back end side from here to here. So whenever is needed changes, so it can go here or it can go here, anywhere it is needed. So spare cells are needed, and ECO cells are also getting used here in this part. This is a gross kind of idea of what is a pre-mask ECO and a post-mask ECO. Now let's have a detail of these two. We're done here. Let's move on to the next slide. Pre-mask ECO. The pre-mask ECO flow can be divided into 6 main steps. First one, describe an ECO specification. Next, capture the specification. Next, compare the ECO netlist with the design net. So here we are looking forward for the changes, and here we have the ECO netlist as per our changes. Pre-mask ECO, and we have the original design netlist which we have already designed and which may come out with bug, and hence we are correcting them with the ECO. These two should be tallied. Next, update the placement with ECO changes. We said the placement right in the previous slide. Placement stage. Here we implement the ECO. Perform the ECO routing. So ECO needs additional routing because we are making changes and that the changes were not originally there. So we have incorporated the changes and also we have to incorporate the routing in the BOL layer. Next, we insert the pillar cells. This is the pre-mask ECO in a nutshell, what we do in a pre-mask ECO flow. And now we are done here. Let's move on to the next. Post-mask ECO flow. Post-mask ECO using conventional spare cells. The spare cells are used. We will talk about the spare cell in detail in later on this video. Describe and capture the specification. Next, we compare the ECO netlist with the design netlist. This is common because obviously we have to compare our ECO related netlist and the original design netlist so that we have a diff between the two. So we are well aware that what we are going to change. Next, check the feasibility of the spare cells. Carry out the spare cell mapping. That means where we should be using what and what type of functionality. We'll understand the functionality once we describe the spare cell later on in this video. Next, perform the incremental routing and fix the routing DRC. Next, we perform the formal verification. These are the steps of the post-mask ECO. The more you get aware with the physical design flow, you will be more understanding the ECO flows. So here we are done with the nutshell description of the post-mask ECO flow. Let's move on to the next slide. Types of ECO by design stage. So far we have talked about the ECO in terms of the pre-mask or post-mask. It's a gross thing. Now let us see in an explicit manner. You have seen already the design flow, that is the ASIC design flow in a couple of slides back. And in this slide we will show you equivalent ECO representation. That means what ECO is done where. So let us start. So this is our front end part. Next we have the back end and then we go for the manufacturing. So you can correlate with our ASIC design flow on a couple of slides back. Here with the front end part, back end part, I have just elaborately marked where the front end ends and where the back end begins, and the manufacturing. Manufacturing is nothing but goes near the tape out zone. Next we have the RTL Verilog, we have the netlist Verilog, we have the placement depth. Placement depth is related to the layout. We have depth and left. Sometimes we also have the GDS2. Here we have the layout GDS2. So here I make a segment and I make a segment here. Why? Because this part is mostly the front end part, this side, and this part is the back end part, and this part is the manufacturing. There are three parts have been defined: front end, back end, and manufacturing. ECO is not very easy to understand and it takes time to understand about the ECO because this is the toughest challenge of a VLSI physical design engineer. Now here we have the types of things. That means if we go towards this right here, this point, the front end design, what we do, we have the base layer frozen. That means we have the FUL frozen. But what happened, right? And then here we have the for the production, it goes near the tape out, right? And in between we keep on iterating from the base layer frozen up to the silicon while we traverse from this side to this side, or ECO if we move from this side to this. Next, we have the RTL ECO. You can see why I have marked with this line. The RTL ECO is related with the RTL and the front end part. Next, we have the netlist. So netlist means this is a synthesized netlist, right? Synthesized Verilog. So we can have a netlist ECO, and this netlist ECO goes even in the backend design, right? Here, because backend has started, there we are using the synthesized netlist. So the netlist ECO can be somewhere in between this zone. And finally, we have the metal only ECO. So once everything is done right up to the netlist and there is nothing left to do in the netlist, what we do? We do the metal only ECO, which is related to the manufacturing and which is residing somewhere near the tape out zone. So metal only ECO is completely on the PUL layer. However, the netlist ECO can be the changes there could be in the FUL layer, FUL or MUL layer. But the metal only ECO must reside in the PUL area. There will be no changes in the FUL or MUL. Next, we have the functional ECO. So here functional ECO can be done. Functional means that the function of the design needs the ECO. That can be in the entire spec. And if we look for the timing ECO that is related with the timing, we'll show you how many types of analysis are there upcoming slide. Functional ECO can stay in the whole range. That means the design specification and its function, whether it is performing correctly. So that has to be checked throughout, whether we are doing the RTL ECO, whether we are doing the netlist ECO, or whether we are doing the metal only ECO. That means the pre-mask ECO or the post-mask ECO, any ECO. So here we are done with the very categorized description of the ECO, and let us move on to the next slide. Types of ECO based on the analysis. Now in this slide, we will categorize what type of analysis are performed on the design to find out the zones which need the actual ECO. Because whatever we have to do within from our design flow and using our tools. So here is our topic, ECO by analysis, and there could be timing ECO, that means through the static timing analysis tool. Next, there will be power ECO. It is maybe throughout the PNR tool, because we do the power routing and all, right, through the implementation tool or the physical design tool. Next, go for the clock ECO. It's also using the physical design tool. Next, we have the metal only ECO. This goes into the BUL only. Decide at the extreme end, I have shown in the previous slide. There could be various types of analysis, that the timing analysis, the power analysis, the clock analysis, the metal analysis. Even for power, there could be IR and EM checks. So those tools also nowadays have this kind of detection. And obviously, since we are talking about power ECO, our physical design tools, there is the PNR tools and all, they also have the ECO flow inbuilt. But there comes a thought for a VLSI engineer that we have to be over sanguine. That means we have to 500% confirm that there will be no bugs remaining in the silicon when it is going out for the foundry. We have done the categorization of what types of analysis are used to detect the ECO related need. Now in the next slide, what we'll do methodology that a engineer implement. ECO target detection through analysis. Through analysis is through the analysis tool, and this target detection is done by a mechanism by the VLSI engineer. And how the engineer does it? First, we have all the prerequisite, like we have the netlist, layout, left, def, and all other files, whichever is needed by the tool that we are using. That is the tool under consideration. Next, we have the first EDA tool from vendor 1. And we have the vendor 2. Okay, we are using a IR drop tool, right, which has a inbuilt ECO, and we take it as a vendor 1 tool. And we take a similar kind of IR drop analysis tool from vendor 2, whether it may have a ECO inbuilt or not. However, we have to be over sanguine about the violation, that means coming from the first tool and the second tool. When all these violations are there side by side from tool 1 and tool 2, we do the compare, tally, and scrutiny of all the violations. And if there is an odd man out among these two set of violations, we have to do the root cause analysis, why that odd man out is there. And there could be some things that is present here and not present here, like that. All these types of QA checks, that means the quality assurance or the quality control checks, that is QC. All these things have to be done by a VLSI engineer. And once we have the confirmed points on which we need the ECO, we proceed towards the actual ECO. So we used one tool. It may be a timing tool, IR drop, or a PNR tool, which have the inbuilt ECO, and it gives the ECO violations. And here we have another tool which may have a ECO or may not have a ECO. However, it also produces violation while working on the same design. And these two set of violations are compared, and we become over sanguine by comparing them. And then we fix our target for the ECO and we proceed towards the ECO. This is generally a VLSI engineer does to save his job as well as save the design before it goes out to the silicon. Here we are done with this particular slide. Let's move on to the next slide. Various ECO cells. So far we have talked about the ECO methodology, detection, and where it is done. So ECO requires some ECO cells. That means some cell we have to put, rectify the design bugs where our functionality is not. So to implement the functionality, we must have some functional cells which can actually accommodate the ECO related physical design changes in the FUL, BUL, or MUL layer. In addition to that, our main design function, that means the input and output of the design, should remain as it was designed in the initial design specific. That's why the ECO cells are specially designed. So let us take a tour. Generally, redundant standard cells known as pair cells are used to realize the ECOs. However, these cells suffer from a major drawback, having predefined functionality and location. As a result, their use becomes limited. To overcome this inflexibility, gate array type pair cells are used. So here comes our pair cell to the rescue. As the gate array pair cells are configurable, it opens up new possibilities of doing ECO. So here we have talked about in general what types of ECO cells could be there and why they should be there. Now let's go specific on the next slide. Pair cells. Pair cells are like most standard cells and have a fixed functionality. Appropriate combination of pair cells of various functionalities are chosen to ensure the desired functionality is available when an ECO modification is exercised. Special cells called pair cells are there in your PDK or the design kit. In case you do not know about the PDK or DK, we have already one episode in our FAQ series. Please go ahead and watch that. Apart from this, some standard cell may get converted into pair cells to meet ECO design related changes. Pair cells which are tie high and tie low contribute to leakage power. Tie high and tie low are necessary to avoid direct connection between power or ground nets to avoid electrostatic discharge event. This is needed. ESD is a very dangerous thing. We have to overcome it. Unused pair cell block unusable area in the chip. They block. Hence, number of unused pair cells should be reduced. We have to use them efficiently. So these are the pair cells. Now let's move on to the next type of cells, that is reconfigurable cells. As per the need, these cells can be reconfigured into a design logic to perform the ECO modification. Unused reconfigurable cells are default reconfigured into decoupling capacitors. So this can be changed into decap, that is decoupling capacitor. This leads to a more efficient use of the available area and the IR drop becomes more significant. Decaps can be used to address that. Reconfigured into any desired logic function, and if they are not used, they can be in the decap form, which actually contribute for the IR drop mitigation. It's a multifaceted cell. Another advantage of the reconfigurable cells is that tie high and tie low cells are no longer needed and hence the reduction of the overall leakage power. So leakage power was a problem in the previous, that is the pair cells, and this is not the problem in the reconfigurable cells. We are done here with the reconfigurable cells. Now let's move on to the next slide. Metal-Configurable gate array cells. Reconfigurable cells lags in the situation when the cell is higher complexity and or different driving capabilities are required. Multiple reconfigurable cells are needed to be interconnected. This adds extra delay that include timing degradation, that means the performance degradation. Solution to this could be the both reconfigurable cells for the more simple logic and pair cells for the most complex logic ones together. So this could be one solution. And another solution is that we have a metal-configurable gate array. That is what we are having here, also known as the GA reconfigurable cells. They consist of an array of tiles where each tile represents a basic reconfigurable cell. If a more complex logic is desired, multiple adjacent tiles can be used, and hence the timing related degradation that we were earlier having will not be there because they are designed like tiles and we can use them for a more complex design. So in a nutshell, we have talked about 3 different types of ECO cells, and here we are done. So let's move on to the next slide. Thank you very much for watching up to this point, and don't forget to like, share and subscribe. In case you have some dislike, put that as in words in the comment section down below, and bye for today.